All right. So far we have just understood how to calculate expected value and how to calculate this. So three things we have considered, and then there is a normalized value of this coefficient, which is a much easier to understand kind of a metric, right? But how do we actually use this information is something that we are going to expand on today. So there are three main uses. Again, there can be n number of other usages, and of course that's where the finance as a field gets much complicated. You can make more rigorous statistical models based on using the information that you have here. But just three simple ideas. One is something called investment risk profile. If based on this information, can you draw a risk profile? Risk profile by I mean that what is the chance that you will lose money? What is the chance that you will make at least 10% of profit? What is the chance that you will have NPV of this kind of a profile you can generate, right? So far you have just a estimation of EX and sigma X. It does not give you an idea of still the chances of making profit in a particular investment, right? Then acceptable investment diagram. So risk profile overlapped with your acceptable investment profile. You can make a judgment whether a particular risk profile is actually helpful for you to make decisions or not, right? And then sometimes even after both these two, you will not be able to have a clearer idea. So there are these thumb rules, which we also call auxiliary decision criteria. These are essentially to guide you using some simple principles of selecting among alternatives. Again, these are very subjective. An individual investor could have n number of different auxiliary criteria. These are some of the most common ones that are easy to understand and we'll look into the course, right? So variance based, most probable, future, and aspirational level. I will just introduce the three, four terms to you. All right. So first, let's look at this example. I think some of you also got confused yesterday. So far I have covered two types of trees. In this tree structure, you see the first probability is related to the annual return, and the second probability is related to the duration of the project, right? In the other example that we saw, this tree structure was cash flow in year one and then cash flow in year two. So it could represent anything. It does not have to correspond like one-on-one to the cash flow series, right? This node structure is slightly different compared to the cash flow representation. Here I'm talking that there's an annual return. So the moment I define an annual return and the moment I define the number of return periods, you know the cash flow series is complete, right? That's what basically this information is consolidated here. So let's look at this example. You have a 10% chance that your annual return would be 10%, 50,000, 70% chance that your annual return would be 100,000, and then a 20% chance that your annual return would be 125,000 rupees. And given these conditions, there is a 20% chance that duration of the project would be 2 years, 20% chance that duration is 3 years, 50% chance that the duration is 4 years, and 10% chance that duration is 5 years. And this is same. MARR is given to be 9%. Okay. So this is the structure that we are trying to solve. Again, in this case, we will go branch by branch. Right. So the probability of this branch becomes 0.1 into 0.2, which is 0.02. And if you were to calculate the net present worth of this particular branch, your cash flow series will become like minus 200. You are talking about 50,000 annual return for 2 years. So whatever the present worth of this particular cash flow series is coming, that will get finally multiplied by this number, right? Similarly, if you were to calculate, let's say for this particular branch, your number of years here are 5 and your cash flow is 125. Right? And then this particular tree or the branch gets this value, whatever the present worth of the coming of this particular cash flow, and you multiply it by probability of again 0.2 into 0.1. Got an idea how to solve this tree? Now what I've done here in the table is I have written these 4 columns. This individual probability is the probability of each of these trees, each of these branches. So 0.2 into 0.1, 0.2 into 0.1, 0.5 into 0.1, and so on and so forth. And corresponding value, the present worth of the corresponding value. But in addition to that, what I have done, one more thing is, I have sorted these present worth in an ascending order. So the least negative or the most negative value is on the top, and then the most positive value is kept at the bottom. Okay, I have sorted this particular table with respect to the PW of outcome from minus to increasingly positive. Okay, this corresponding probability will come anyhow. So this does not have to follow. This particular column is not exactly the same order as this. Okay, that's what I am implying. Now, if you want to take the weighted outcome, you can simply still multiply this column with this, and you will get these values. So that's not a problem. But what I'm trying to do is, I'm plotting a cumulative probability distribution. I have a distribution of individual probabilities. I'm now making a cumulative probability distribution. And whenever you are making this cumulative probability, you have to have some sort of a ascending or descending sorting order. You cannot calculate cumulative probability without that. You should not. You can, but that's wrong. Idea is that you sort your series from increasing to decreasing or decreasing to increasing, whatever the order is, and then only you calculate the cumulative probabilities. So what is cumulative probability? This is 0.02. Then next one becomes 0.04, which is this value plus this value, just simply added. Then the next value is this value plus this value. So it's coming out to be 0.09. Then this value added to 0.14, so you get 0.23, 0.24, 0.28, 0.42, 0.46, 0.81, 0.88, 0.98, and 1. Clear? How did we calculate the cumulative probability? Now what you can do is, you can plot the cumulative probability on y-axis and the present worth on the x-axis. There will be some approximation because this scale, of course, is not a uniform scale. So what I've done is here, just assuming that I have just kind of discretized the scale, but you could also plot in a continuous basis, not a problem. You could actually make a scale from minus 1,20,000 to plus 2 lakh or 3 lakh or something, and then plot them exactly, not a problem. So the curve will become slightly smoother. That's it. But just for the concept, I've shown you here. And now the cumulative probability will give you this idea. So minus 1, 1, this first series, the cumulative probability is 0.02. Right? Then the second series is minus 73,000. The cumulative probability is 0.04. 38, 0.05, and so on and so forth. Right? Now you know, if you want to know, for example, what is the chance that your risk, that your investment will actually give you a profit. So then you can draw a line somewhere over where the cash flow becomes just positive. So ideally this point will come somewhere in between, the way that we have plotted. And then you can read the corresponding value. In this region, you are making losses because your probability or the PW is less than 0. In this region, you are making profits. So there is about, in this investment profile, there is about 30% chance that you will lose money, and there is about 70% chance that you will make money. Right? You could also do some different analysis. You could simply say, let's say, what are the chances that my investment will generate at least 50,000 rupees. So again, you drop the line there. It gives an idea that there is about 55% chance that you will gain at least 50,000 in this particular investment. Right? So what we have done is, essentially, using the probability distribution of this whole, we first estimated, one thing is you can estimate the expected value and the sigma and whatever, but without doing that also, you can calculate what is the probability distribution of the whatever your final variable that you are interested in. Present worth, annual worth. You could do also this for annual worth. You could do also for future worth. And then you can generate a profile and then give an idea, okay, in the probabilistic way, there is a 40% chance that in this investment I will make a money out of it or not make a money out of it. Right? Got it? Is it clear or confusing? Clear? Alright. So let me show you more variations of the same problem. So in this case, there is this is a state investment risk profile, right? And we are only interested in a very simple calculation. Simple calculation is that we are just worried about a single line. What is the chance that there is a at least profit? What is the chance that the PW is at least 50,000 and so on and so forth. But you could have a more complex desire from an investment that it should not generate. The probability of it getting zero money or less than zero should not be lower than this or higher than this, and the risk should not be too high and things like that. So you can have multiple criteria combined into a single statement, and that is something called a acceptable investment diagram. So this particular curve is the outcome of the cash flow series, right? But you can also plot your acceptable diagram on the similar kind of a graph, and then you can graphically compare whether the outcome that is coming out of the cash flow series is matching your requirements or not. Okay, I'll show you that how. So an investment of $1,000 for 1 year has the possible after-tax return. This is shown in the table. The probability of each outcome is also given to you, and the rate of return is apparent and shown in the table. So there is a net. If the net return is 900, the original investment was $1,000. So you mean that you have made minus 10% of return, right? And the probability of it outcome is already given to you, 0.005 in this particular case. Now, pay attention to this part. The investor seeks proposal that provide probability of 0.95 that they will not lose more than 5%. So they want an investment with a probability of at least 95% that they will not lose more than 5% on their returns, or their returns should not be less than 5%, those kind of thing, at least in 95% of the cases, and a 30% likelihood that their rate of returns will be greater than 15%. So it's a slightly complex criteria, not a simple criteria that we saw. But essentially the idea is that you plot these two, what is my requirement versus what is the outcome of a series, cash flow series, in a single diagram and then compare. Okay. So use the acceptable investment diagram to determine the acceptability of this $1,000 investment proposal. So you want to make a judgment whether this particular investment, the returns for which has been given in the table, is it acceptable to you or not, right? So what I'm doing here, the net returns have been given to you 900, 1050. These values are simple. Since the base is $1,000, the percentage of return immediately becomes clear. 10 minus 10%, 5%, 15, 30. And the probability of outcome has also been given. Now again we have to plot the cumulative. For cumulative we need to sort it out, but this is already sorted, so no need to worry about it, right? Now pay attention here. Since we're talking about not about making money, but we are more likely about not losing money. So therefore I have calculated the cumulative probability in a reverse manner, not in a same like simple like adding from here to here, but basically trying to go from top to down. Simple. To keep it simple, you could reverse it also and then plot your diagram accordingly. So if the outcome probability, there's a 5% chance that your rate of return will be minus 10%, then there is a 95% chance that your rate of return will be greater than minus 10%. Right? That statement makes sense? Similarly, if your rate of return is, there is a 15% chance that there's a rate of return is at least 5%, then 0.95 minus 0.15, at least 80% chance that your rate of return would be greater than 5%. Making sense? Basically cumulative probability, but then I'm subtracting this from 1 and just trying to gradually keep on subtracting, so you generate this kind of a profile. Making sense? Now you simply plot the rate of return and the probability on the curve. So this particular blue line is what we are getting. I'll show you some of the points. So again, this is not a continuous, you can make it continuous rate of return, not a problem. Here is the cumulative probability equivalent. Here is the rate of return on the axis. You can make it more uniform. That's not a problem. But assuming that, so first is minus 10% chance, and there's a 95% probability that it will exceed. So there's a 95% and minus 10 in the middle of that. You plotted this particular point, right? Then 5% rate of return, 80% chance. So 80% chance, 5% rate of return, right? Then 15% rate of return. The probability that rate of return will be higher than 15% is 0.4. So that comes here, 0.4 and 15% rate of return. So this blue line is something which is getting generated by the series that has been given to you, right? Now you have two more conditions. One is you want a profile that there is at least a 95% probability that you will not lose more than 5%. So on the same graph, you locate the 5% and 95. You will not lose more than 5%. So this is basically somewhere minus 5% you are looking for. That is the point which is of interest to you, right? And then something, the 30% likelihood that the rate of return will be greater than 15%. So again, 30% likelihood that the rate of return will be greater than 15%. Got the point? Now you just, this is again, of course, in between there could be a lot of variation. We are assuming a uniform distribution within. So as long as your investment profile is higher than this black line, your whatever the diagram is on the blue is acceptable to you, right? And here you can see that in certain part here, except for this certain part, this investment is likely to meet your requirements because it is giving you at least what you are desiring from it, right? And here this is mostly coming again because you are plotting it on more of a uniform. If you vary your assumptions slightly and all, you can always accept this, that this is a good enough investment for you. Again, if you don't want to accept this particular point also, you can have more refined criteria to accept or make a decision on whether to accept it or not. But the idea remains simple. How do you use the expected value and the distributions that you have generated for actually making decisions whether a particular investment is making sense to you or not? Okay. So what did we essentially do? We are essentially doing if the input variables, whatever the input variables, let's say in this particular case is the net return, based on their probability distributions, we are first estimating the probability distribution of the outcome, right? And then making the decisions on that. Outcome probability distribution we have plotted on a cumulative scale, and that's what we are trying to do. In the previous case, the outcome was the present worth of this whole tree. In this particular case, the outcome is also on the return side, but you are combining the probability and plotting it on a single diagram. We will just, in today's class, we will just see different variations of the same game under different conditions. Okay. In this case, there are no assumptions involved. You are not assuming the probability distribution of outcome. You are deriving it from whatever the input information has been given to you. You are not assuming anything that outcome probability distribution is going to be like this. You are exactly plotting of what is expected given the series that is given to you here. Okay. Let me show you more complex examples. But before we go, I'll also introduce this auxiliary decision criteria. As I told that sometimes you can plot all these nice graphs, which is good, but again, for certain specific issues, you might still require certain thumb rules. And that is always prevalent. And of course, the more experience you gain, the more different kind of thumb rules you develop on your own. Some of the common ones I'm going to introduce you here. There's something called expectation variance, most probable future, and an aspiration level. So expectation, the variance related thing is that as an investor, by default, you want to your desire is to minimize the variation, minimize the variance. Okay. In the most probable future, you have or you kind of make an assumption the investment that has the greatest return is the most probable future. So you are much more optimistic about the future. Whatever you think is the greatest probability, you will assume that that will happen for sure. If there is a 5-6 outcomes possible, one outcome has a 40% chance, you assume that 40% is going to happen and make your decisions on that. And then there could be some aspiration level. I will show you how to also calculate them. All right, let's look at the variation principle first. So the idea is that you want to minimize the variation. So if two or the more alternative have the same cost or return, if the cost is same, you choose the alternative with minimum variance, right? If the variance is same, you choose the one with the lower cost or the higher return. Make sense? But if both the expected returns and variance are unequal for alternatives, then alternative with both higher returns and lower variance is preferable. Right? You are basically trying to maximize your returns, lower your variation. That's what this principle does. Seems simple, but even these three rules will not be able to help you out in getting alternative selection all the time. Okay? So, for example, let's look at example here. So, let's say this is alternative A, B, and C. The possible net present worth of these is -1000, 0, and their probabilities has been given to you. So this is the input information. What the probability that this alternative A will give you a net worth of $1,000 -1000 is 0. It will give you a net worth of 0 is 0.11. Similarly, it will give you a net worth of $4,000. The probability is 0.39. Right? Similarly for B, similarly for C, the output has been given. Based on this information, you can easily calculate the expected value, and you can also calculate the standard deviation. This is E, this is sigma. Right? I've shown you the formulas on how to calculate that. That's not a problem. So which one you would choose? Between A and B. Why A? Higher return, lower variance. Right? So that's a pretty simple decision. Between B and C, what is happening? B has higher return but higher variation. C has slightly lower return but then lower variation. Variation is essentially how pinpointed your decisions are. Those like how narrow that band is going to be. So you are more likely to remain closer to the mean value, but then the mean value itself is lower. So how do you judge? Right? So this is where even this minimum variance criteria cannot give you answer always immediately. In certain cases, it will immediately give you. If the cost is same, minimum variance. If the variance is same, lower cost or higher returns. Or otherwise, you try to maximize your returns with lowest variance. But again, it's not sufficient all the time. And therefore, you might use other auxiliary criteria. For example, you can define that first I will look at the variance. So based on variance, I am immediately clear that A and B, between A and B, A is better. B and C, I am not 100% sure, so I will look for another criteria to select this. This could be another auxiliary decision criteria that people often use is something called most probable future. So what do they do? According to this criteria, the investment that has the greatest return for the most probable future is preferred. So for A, what is the most probable future? $4,000. So A, 0.39, probability is $4,000. With B, what is the most probable future? $4,000 with a probability of 46%. And with C, what is the most probable future? $2,000. So this becomes between A and B, which is preference according to this? B, because it has 46% chance, which is 7% higher compared to for A, right? So in this particular case, B becomes a better alternative and both of them are simultaneously better than C. So in first criteria, you generated A is greater than B, and between B and C, you were confused, right? Here you generated B is greater than A, but both of them absolutely greater than C. C is out of the question here. Still not 100% clear. So you could add more criteria. Again, there's no end to it. Ultimately, you have to justify yourself why are you choosing particular thing, right? So in this case, we talk about something called an aspiration level. So this could be n number of things. For example, similar to the AID diagram that we saw, this particular diagram that we saw, this is essentially your aspiration, that I want probability of this to be at least this and this probability of this to be at least this and so on and so forth. This is essentially your aspiration level. So you can also use those kind of criteria. For example, in this case, suppose my minimum amount that will satisfy the decision maker. So if my aspiration is to make some money, it means the probability of that this investment will give at least some return positive greater than 0. So for A, what is that return? It's essentially 0.26, 0.22, 0.02 and 0.39 summation of that. There's an 11% chance that it will become you actually 0 return, and there is a 0% chance that it will give you negative return. So for A, there's an 89% chance that it will have some worth which is greater than 0. Similarly for B, that worth is 0.07 and 0.46, 0.53. Alright, and for C, this becomes, this goes away, this, so that becomes to be 0.76. So with this, you choose A greater than B, no, A greater than C, greater than B. The more criteria you make, the more differences you will have in your decision. Ultimately, you have to decide which is the criteria that you like, and you can choose accordingly. You can combine multiple criteria to tie break under tiebreaker situation. For example, one way to look at this whole thing could be, first I will look at the variance. Within variance, I have already made a decision, but then I only need a tiebreaker between B and C. So next time, in the most probable future, I'm only comparing B and C. I'm not comparing A and B at all, right? That could also be a way for you to break the tie. But ultimately, whether you like the variance best, most probable future the best, you are giving more high priority to the variance or the most probable or the desirable outcome, it all depends on you. You decide that priority. Okay? And then you can break the tie, use these multiple criteria to get some information. Alright? So far with me, I've given you multiple ways on how you can combine the input probability to make decisions on the output side of it. Right? First, estimate the probability of the outcome that you are interested in, and then make decisions on them. The problem is not finished yet. There are many more variations of it, and I'll just show you 2-3 more examples. Mainly because this real world has no one particular method for you to select, so you should know what are the possible range of options, and then you can use them according to your wishes. Right? There's the other simplified way to look at the picture, I would say. So imagine this is the kind of cash flow series that you have. X0 is the initial one, X1, X2, Xn, and each of these are random variables. And by random variables, I mean that they are, X1 is a variable that can have some probability distribution, X2 is a variable that can have some probability distribution, and they are independent of each other. If X1 changes, it does not have necessarily an impact on X2. X1 and X2 can vary independent of each other. In that case, that's a very specialized and very simplified case. Real world will not be like that. As I gave you examples, it could be that if your cash flow in the first year is higher, you can use that profits to invest in your business and maybe increase your profits in the X2, right, year 2. So real world, there is a correlation between cash flows occurring at multiple time intervals. But here we are assuming that all these are varying independent to each other, right? In that simplified case, you can, again, the target outcome is whatever the present worth, we want to estimate the probability distribution of that present worth. All right, that's the target problem that we're trying to solve. So there is a X1, so there is an expected value of X1, and there is a sigma 1, which is the variance for sigma 1. Similarly, there is an expected value of Xn, and there is a sigma n. That is how they are defined. Okay, so using this information, how do you make the estimates about probability distributions of present worth or whatever the annual worth, and so we are going to, I'll give you an example. So your present worth formula is simply this: x0 plus x1 upon 1 plus I, x2 upon 1 plus I square, xn upon 1 plus I to the power n. This is straightforward, nothing new. Expected value of present worth. Essentially, expected value, I'll give you a formula here. It's, I think all of you know this. So this relationship hold to the expected value of A being a constant multiplied by the variable X, which is the random variable, is equal to the A comes out of the bracket multiplied by the expected value of the X, right? So with that, your expected value of the present worth will easily become, the first is mu naught, there is no coefficient or nothing. In the second one, the expected value of x1 is mu1, mu is the notation for mean that we typically use, and 1 plus I becomes your what? Coefficient, right? So that just stays outside. Here I is not a random variable. You have to, if I is also a random variable, you are in trouble. Then you cannot use this formula immediately, because then I will also have its own variation, and there will be combined multiple variation terms coming out of a simple expression. Here we are assuming that I is a constant value, right? Second will be expected value of x2, and this 1 plus I square becomes the coefficient in this particular case, or you could say A2 if you are following this notation, right? So you are okay with this expression. The second expression, expected value of present worth is mu naught plus mu1, which is the mean or expected value of x1, divided by 1 plus I, because 1 plus I is the coefficient that comes out of the bracket. Alright. The variance also has this formula. If x is a random variable, which is expected to have some probability distribution, and b is your coefficient, which is a fixed value, the variance becomes, the term b square comes out, and then you can use the variance of whatever the x value. Have you read this formula before? Have you? I think this is a pretty, if you understand this proof, then this is pretty straightforward, that follows from there. Because variance formula was what? Expected value of x minus xi, right? Square upon n square, under root whatever, if you want to take a, no, this is just the value essentially. So then the term comes out in a square manner, right? Alright, so with this we are also able to claim this particular equation. So variance of present worth will become sigma naught square, which is the mu naught value, sigma 1, which is the variance of the series x1, and this coefficient was 1 plus I, so it comes out to as 1 plus I square. Then variance of x2 is sigma 2, and the series, the value comes out to be 1 plus I to the power 4, because the coefficient in this case was 1 upon 1 plus I square, right? So essentially this becomes the series of variance. So alternatively, this is just a simpler way to represent it. This also becomes sigma naught square plus sigma 1 square p by f I2, p by f I4, p by f I6, just to make you an idea of terms that we're talking about. So what we have done is, given that there is some distribution of x1, x2 and x3, we have now calculated under special condition, assuming that x1, x2 and x3 are independent of each other, we have estimated the expected value of present worth of the cash flow series and the variance of the cash flow series. So now we know mu of the PW series, and we also know the sigma of the PW series, right? Now again, once you know this, is it sufficient to calculate probability? Maybe too advanced of a question for probability side, but essentially, are you guys familiar with this kind of a curve? What is it called? Normal distribution curve. Normal distribution curve is defined by two parameters. Once you know mu and once you know sigma, you can define that curve nicely, right? I know mu and I know sigma. Does it mean that it is a normal distribution curve? Ideally not. There's no guarantee that the even if you know the mu, even if you know the sigma, that it is a normal distribution. But that's the specific assumption, particularly only for this problem. And it also has some merit in statistics, which says that if you do a sample, like basically it's a central limit theorem and many things that you can see, but essentially things tend to converge on the normal distribution. Normal distribution curve is very often present in our day-to-day situation. If you do an experiment many times, there's a very high chance that it will actually follow the normal distribution. But there's no guarantee, and we are not going into those details, but there's a specific case of this particular problem which we can solve, assuming that this distribution also follows a normal distribution. That assumption is also valid when individual of these x1 and x2s are normal distributions, then the present worth will also be a normal distribution, right? Under this assumption, when we are solving the problem, based on these values, you can define the probability distribution curve, and then you can use the same thing. Now, if you know the probability distribution curve, you can answer the question, what is the chance that my investment will have at least not negative cash flows, or a 10% chance that my cash flow would be this. All those questions you can answer. How? Let me just show you. Okay. Let me show you an example, then we'll talk about it. Okay. So this is a simple case. Year 0, 2000, it's not a variable. For year 1 cash flow, mu is given, sigma is given. For year 2, mu is given, sigma is given. For year 3, mu is given, sigma is given, right? Assuming that these are also normal distributions, in that kind of a condition, we are solving this example and independent of each other. Okay, so this is the present worth of this will be 1000 upon 1 plus 1000 is the mu for cash flow in 1. It's actually same for all, and this will come out to be your expected value. This formula is okay. Everyone agrees to this? Variance, sigma naught square, there is no variance because this particular is not a random variable, so its variation is 0, its expected value is 2000, that remains the same. So this becomes 0. Sigma 1 is already given to you, is 2000, so this 200, so 200 square upon 1 plus 1.1 to the whole square, and so on and so forth, right? This term is also making sense. So this is the variance of present worth. So the sigma of present worth is this particular value. Now you know E, now you know sigma, you can use the curve. If I ask the question, what is the chance that the above investment will run into losses? What is the chance that you will have a net present worth less than 0? How will you estimate it is the question that you can answer based on the information that we have estimated so far. Are you familiar about a concept called Z-score? Anyone who doesn't know Z-score are hearing it first time. So Z-score is a very special for normal distribution curve. What you can do is any distribution curve like what we have talked about, you can convert into a normalized curve, right? How? You can estimate the Z-score as xi minus mu upon, right? In that case, you have normalized. So for example, what will happen to the mean value? The Z-score of mean will be 0, and Z-score of any random value, let's say 587, will be what? 100 upon this sigma value. And similarly, if it is xi is 387, then your Z-score will be minus 100 upon that sigma value, right? This is how you calculate the Z statistics. It's called actually Z statistics. Now, some very brilliant mathematicians have done your job and they have given you these kind of tables, right? What does it mean? For any value Z, the area under this curve, this is actually a probability distribution. This is not a cumulative probability distribution. But when we are trying about the percentage of house, we are always dealing with cumulative probability distributions, right? That's what we showed earlier. So cumulative probability distribution for such a continuous function is essentially the area under that curve, right? So for any Z value, the area under that curve is, people have plotted such kind of tables which are readily available on internet. So what you simply can do, if let's say your Z score comes out to be 3.42, minus 3.42, you can go to this table, go to minus 3.4 line, and then the next remaining term is what? 0.2. So it means that the area under the curve for a Z value of minus 3.42 would be just 0.003, which will be equivalent to what? 0.3 percentage, right? So in this case, there is only 0.3 percentage chance that the value of this, the value will go lower than this particular Z, right? That's how you read the Z curve. Making sense? This is available all the way. I've just given you a very simple example from minus 3.4 to minus 2.1, but it is from minus 3.5 usually to all the way to 3.5. You can actually get it. Are you guys familiar with the concept of characteristic strength? What is that value? Probability that your cube strength will be at least 95% of the time your cube strength will be a certified particular value. How do you calculate that? Right, that is coming out from this Z statistics. This 1.65 comes from this, the Z value of 1.65, which assures that the area of this curve is 0.95. Okay, so again, depending upon the distribution, this is also very beautifully designed. If your value is lying somewhere here, the area will definitely be more than 0.5. If you are lying somewhere here, the area will be definitely less than 0.5 and all those. But read a little bit. I am not going into details of how to estimate that score. If you still have doubt, ask me. Okay, but it's a very simple operation. Essentially, you need only X and mu, the mu and sigma value, and then you can estimate the answers. So, coming back to the question, what is the probability of making losses? So your X will become what? Losses is less than 0. So X is 0. Corresponding to that, the Z score would be what? 0 minus 487 divided by 288. What is this value? 1.69. 0.0455. So about 4.5% chance, or if you round it off, 4.6% chance that this curve will give you less than 0. Got it? Understand? So again, we have covered quite a lot of things today in terms of how to use the expected value and the sigma to estimate the decision making related variable, the probability of decision making, under which what is the chance that you will run into profit, what is the chance that you will have at least this much profit, and so on and so forth, right? And we again follow this. There is a variability in the input, all the variables. Based on that, we estimate the probability distribution of the output, and we try to make decisions. This is what we have been doing so far. I've shown you multiple cases of how to do it. Under specific assumption of normal distribution, this particular method holds true. Right? So far we have done a lot of interesting things, but I will also leave you with this word called simulation. We have been doing a lot of things manually. We have defined mathematical equations and then individual variables and calculating on our own. But you can actually computerize the whole process, or basically make good simulation models out of it. And a model is nothing but it does is it tries to imitate the real world and expresses the real world in terms of mathematical equations. And once you have the mathematical equations done, you can change the parameters and then see what's the output that you are going to accept out of it or expect out of it, right? So the same thing that we have done so far, we will also have a specific case called Monte Carlo simulations. Okay, we'll know. At least that, I think this is going to be one highlight that you can claim in your resume after this course. This is going to be an extremely important point. Pay attention in the next couple of classes, but I'll set up the foundations. So essentially the advantages of the simulations are, they are really flexible. You can represent any world in mathematical equations, and once you have represented a very complex phenomena into simple mathematics, then it is on your command. Then you can play with it to change the values to see how the world will behave. So it gives you an kind of a virtual laboratory, you could say. Once you have created mathematical equations to represent a phenomena, then you can play with the numbers to see how under different hypothetical conditions it will behave, and that helps you to make decision making more efficient, right? That, and again, very large complex real world problems you can apply it. Simulations are extremely powerful, and at the same time, whatever you do in the simulation does not have to be in the real world. You can make hypothetical assumptions and start just play with the game, and then see how does it will work, so that you're better prepared to deal with the real world. That's the expectation. The challenge is each model is unique, and therefore you need to create multiple models to represent many complex phenomena. So it's quite a challenging task to set up that. And of course, setting up mathematical equations for everything that is happening in natural world or a real world is not as easy. That's where the complexity lies. And of course, this course is not about the numerical simulations, but this course is just to give you an idea that whatever we have learned so far can also be done very important and beautiful way. And we'll have a particular look at something called a Monte Carlo simulations. Okay, and in your projects, you are expected to do at least Monte Carlo simulations level thingy. But it's a point worthy of your CV. So I hope all of you will enjoy the part. Okay.